Great. It's really a pleasure to be here. Thanks for sticking around. Usually I like to get right to the punchline in my talks, and actually Reggie gave it yesterday. Yes, we have found organics on Mars, so that's not a mystery anymore. Although I have to say, before Curiosity, a lot of us on the team were really skeptical that we were going to find anything given the ionizing radiation environment and that kind of thing. And we really felt like it was, searching for the needle in a haystack kind of analogy. Well, we found a lot of needles, and much more than we expected, frankly. And now the challenge will be trying to figure out where the heck these things came from. Just a bit of background. The search for organics on Mars started over 4 decades ago, right, with Viking. NASA put 2 landers down on the surface of Mars. They had a biology package, which I'm not going to talk about, but did want to talk briefly about the pyrolysis gas chromatography measurements that were made on both landers. And it's notable that they found these chlorinated methanes, chloromethane and dichloromethane, and they kind of wrote them off as just contaminants because they used chlorinated solvents on the instrument. They said, these can't be Martian. Even though they never saw these in the blanks, they kind of said, trace levels and probably contamination. So they concluded no organics of Martian origin. Recently, Melissa Guzman and Chris McKay and others have reanalyzed some of the Viking GCMS data, and we're actually seeing even more complex chlorinated molecules, chlorobenzene, which I'll talk about later. And it's becoming clear that, Viking probably did detect Martian organics. Pretty cool. Of course, the Allen Hills 8401 Martian meteorite caused a big stir in the astrobiology community. Frankly, this discovery gave me a job at the time. I was a grad student, didn't know what I wanted to do. And then the possibility of life on Mars just sucked me into astrobiology. Pretty exciting discovery. All the attention initially on this rock were on these, or most of them were on these worm-like fossil structures, that have since, I guess, been sort of disproven that, doesn't have to be biological. I was really paying attention to these polycyclic aromatic hydrocarbons, which you've heard a lot about yesterday. These things are ubiquitous, not necessarily a biosignature. But originally we were thinking that, maybe these could be contaminants from the Antarctic ice. Remember, this meteorite sat there for 13,000 years before it was discovered. But now it's looking more like that these probably are indigenous to the meteorite. Andrew Steele and others at Carnegie have looked at ALH and about a dozen Martian meteorites, and they're finding pretty high amounts of carbon, 20 ppm, the macromolecular material. They believe it's high temperature in origin, non-biological in origin. But anyway, it's pretty cool. So, we thought, there should be organics on Mars. Now, what wasn't clear is whether these organics were in the near surface that could be accessible to Curiosity. But certainly in a Mars meteorite that's ejected from the subsurface, you have Martian carbon. Another interesting discovery from the Phoenix lander in 2008, which went near the polar regions, scooped up some soil, found water, which is pretty cool, but also this perchlorate anion, which is kind of an unusual thing. First time we've discovered it on Mars. This is the stuff you find in fireworks and flares. It becomes very explosive when you heat it, which actually ends up challenging organic measurements that use heating as a way to get the compounds out, like we're doing with Curiosity. And what we think is happening, and this is the same with Viking too, where they take samples and heat them up, is that these perchlorates are combusting basically. They're breaking down, releasing oxygen, reacting with native organic carbon, and then forming these chlorinated molecules. And we've seen this in lab experiments, and now the data from Curiosity is pretty much sealing the deal on this. We know that this reaction is occurring. Okay, so let's get to Curiosity here. Landed in Gale crater. Gale is an interesting spot because it's on this dichotomy of the northern lowlands, which may have been a large ocean at one point, and the southern highlands. And so we think that Gale was a crater lake at one point, full of liquid water. There's really good evidence for that. This is kind of a side view of Gale crater. It's got this huge 5.5 kilometer high mound in the center, which makes it a really attractive landing spot because basically we're getting at the subsurface of Mars, right? We're able to see the history of Mars. So Curiosity landed about here, and then the idea is to drive up the mound, exploring the history of Mars, trying to figure out what happened during this transition from a warm, wet environment to now the cold, dry environment that we know Mars today. So this is all really exciting, and we landed, thank God, 7 minutes of terror. For me it was like 20 years of terror because I'd already spent 10 years working on SAM, which I'll talk about here in a moment, and then this mission will go 10 years for sure. So there's Curiosity. Hard to see with the lighting, apologize, but loaded with instrumentation. I mean, this really is an analytical lab on wheels. And I'm going to focus primarily on the SAM instrument, which lies in the belly here, which is the most complicated instrument ever sent to the surface of Mars. So, and again, the goal here is to look for organics and volatiles and try to understand, in general, the volatile distribution on the surface of Mars. And we've gone about 20 kilometers or so. Here's where we landed. And again, this is Mount Sharp here. So the goal is eventually to get up into these clay and sulfite units. Here is this transition, we think, between the warm, wet Mars and the cold, dry Mars. All these red dots are holes that we've drilled. One of the interesting things is we drilled in this Lake Mudstone, Yellowknife Bay here. And immediately, colors aren't too great here, but red Mars became gray Mars, okay? So before this entire surface looked red, oxidized materials, not good for organics preservation, frankly. Once we started drilling down into some of these mudstones, it was gray. And just by the color, you can tell it's a more reducing environment and better for organic preservation. So that was good news. I'm not going to talk about all these drill holes, but I do want to note that Curiosity, as of yesterday, today, officially, we're back in business. We were kind of down because of a computer glitch. And we're drilling again. So we've now drilled, there's 17 holes here. We've now drilled the 18th hole on Mars. So excited to get some of that, start feeding SAM again, and looking for organics. Okay, so this is SAM, again, a microwave oven size instrument, very complex suite of instruments. The heart and soul of this is really a quadruple mass spectrometer, which we use to identify individual masses of volatiles that we release from the sample by heating. We have a gas chromatograph system provided by the French that allows us to separate complex mixtures of organics. And then a tunable laser spectrometer. I'm not going to talk a whole lot about that. That was built by JPL. Can measure isotopes of water and CO2, but I think it's most known for the methane detections that have been made in the atmosphere of Mars, which is pretty exciting as well. We have a carousel that can hold up to 74 samples. So, we've got 18 drill holes. So. We got plenty of room for more analyses here. Okay, just briefly how it works. We heat samples up to 900 degrees C, release the gas. We can sniff the gas directly in a quadruple mass spectrometer, and we get what's called an evolved gas analysis. So we measure different volatiles by their mass as a function of temperature, which tells us about the bulk chemistry. I'll be talking a little bit about that, and also the gas chromatography mass spectrometry measurements where we can separate out individual compounds before they're sent into the mass spectrometer. So very, very useful mode. And I'll just point out that Viking heated to about 500 degrees C, and we're getting to much higher temperatures. And this was actually important for the detection of several organics that Viking wouldn't have been able to see because it didn't heat the samples high enough. Okay, so this is a complex EGA, but basically you got sample temperature on the bottom and counts per second by the mass spectrometer, the function of mass on the top. I just want to highlight a couple of things. There's a lot of complex bulk chemistry. We see water and SO2 from the decomposition of sulfate minerals. But what was really interesting with this Yellowknife Bay mudstone is we saw this sort of anti-correlation between O2, which was going up and dipped down like it was being consumed, and CO2. And although everybody was sort of afraid to admit it when we first saw this data, we're like, this is organics combustion. And everybody's like, ooh, can't be, yes. And actually quite a bit. I mean, we're talking about, tens of ppm and more of organic carbon here. So this is pretty exciting. We see NO from nitrates. Again, the O2 here we think is from this perchlorate decomposition, providing the source of oxygen. And then we see these chloromethanes again. And of course, not really talked about, we hear about methane in the atmosphere, but we also see methane coming out of the rocks itself when we heat it, probably a decomposition product of heavier organic. Okay, so let's just get right to it here. This is data from the evolved gas analysis. So we're not talking about insignificant amounts of carbon here. I mean, we're talking about several hundred to 2,400 ppm. Okay, you find similar levels of organic carbon in the seafloor sediments in the South Pacific Gyre, for example, which provides enough energy for up to 10 to the 5th cells per gram. I'm not saying that we've got bacteria on Mars or anything like that, but if there was life 3.5 billion years ago, this carbon source would have been enough food to support that kind of community. So pretty cool. Again, most of this is combusted organic carbon. I'll talk about some of the reduced individual compounds here in a second. But it's there. Most of the organic stuff is coming off at low temperature here. We do see some potentially higher temperature organic carbon as well as some inorganic carbon, probably from carbonates. Okay, so I mentioned chlorobenzene in the Viking data analysis. Interestingly enough, the detection of chlorobenzene by Curiosity is kind of what spurred those revisiting the Viking data analysis. So they kind of knew what they were looking for, so it was easier to spot. But we found really high levels, and this is Cumberland, one of the mudstones in Yellowknife Bay, 150 to 300 ppb. And these are the kind of levels in the soil that we saw. This was kind of on the order of what Viking was seeing, down at the part per billion level. But again, enormous amounts of chlorobenzene, and not in our blanks, not in other samples. So this is not something that we brought to Mars. This is Martian material. So where is this chlorobenzene forming? How is it forming? One of the hypotheses that Benner put forward way back in 2000 was that any reduced organic material, whether it was delivered to the surface of Mars by IDPs, comets, or meteorites, or somehow indigenous, maybe associated with a biota at one point, eventually this stuff will oxidize. Water itself will photolyze UV, forming these radicals, which basically chew up the organics, oxidize it over time, forming these oxalates and acetates and benzene carboxylates. And Benner predicted that actually you could get quite a lot of this stuff accumulating in the surface. What we think is happening is that we've got this kind of stuff there, and that when we heat this stuff in the presence of perchlorates, okay, that break down, we can form these chlorinated benzenes. And so this has been confirmed by lab experiments, and we think right now that's the best explanation for why we're seeing chlorobenzenes. Okay, so this is also really cool. For a while, all we were seeing was chlorinated compounds, and nobody really liked that because we knew they were products of combustion with perchlorate, and what does the native organic material look like, and all that. Well, this was the first time we saw non-chlorinated compounds. And what makes this result special, this was published by Jen Eigenbro just recently here at Goddard in Science, is that these materials, these sulfur compounds, are coming off at high temperature, above 550 degrees C. Okay, so definitely not something from the instrument background. These are materials that we believe are breakdown products, potentially of a macromolecular, a heavier organic component. So again, when we heat this stuff up, we're fragmenting this stuff into pieces, and we're seeing the fragments. So it's a bit of a puzzle to try to figure out what was originally there. But this is really exciting to get these sulfur compounds. Again, this is the GCMS data. So seeing this now for the first time, we see these thiophenes and methylthiophenes. Dimethylsulfide is interestingly enough on Earth, DMS is one of the most abundant biological sulfur compounds. It's released into the atmosphere. So not saying this is biological, but just wanted to point that out. It's kind of interesting. So again, trying to figure out whether these things are biological or formed by non-biological processes is not a trivial thing, and we're working hard on that. Just to give you an idea of how hard this challenge is. So on the top, you're looking at a GCMS analysis of the Murchison meteorite, which we heard about in the last talk, after heating it to 600 degrees C. So, again, all this macromolecular material that's in this meteorite is basically breaking down into, hundreds of different fragments. And you see the same kind of pattern in biological kerogens on Earth that have been, thermally altered and oxidized over time. So trying to discriminate between, a kerogen-like material of non-biological and biological origin after process, this is hard. Okay, this is definitely hard to do in situ, hard to do in the lab, but this is kind of where we're at. So we've got organics, don't quite know the source yet. Another thing that complicates the story is cosmic radiation. So Mars, doesn't have the magnetic field that the Earth has, so all of that harmful, high energetic radiation, both UV and ionizing radiation, can penetrate, and in the case of galactic cosmic rays and solar cosmic, can get quite deep in the surface, down to a meter or more. And this stuff just obliterates organic matter. So Again, complicating our ability to search for organics. Now, one kind of saving grace here is that Sam was able to measure the cosmic ray exposure age, which was kind of cool. We never even thought we could do this when we built the instrument, but Ken Farley and others at JPL figured out a way to look at helium-3, neon-21, and argon-36 that we're measuring by SAM to determine how much cosmic ray exposure. It turns out those mudstones that I talked about earlier only have a cosmic ray exposure age of 80 million years. That may sound like a lot of time, but remember these sediments are 3.5, 4 billion years old. So actually 80 million years is not too bad. So that may be helping us here. Okay, so we've got organics, probably some macromolecular material. 5 minutes, oh my God. Okay, I gotta hurry up. What we're really interested in is looking for biosignatures, amino acids, for example. This was work done by Alex Pavlov back in 2016. What he's finding is a little bit discouraging. He's showing that when you mix glycine in the presence of silicates and you expose it to, in this case, gamma radiation, you can decompose this stuff pretty quickly. So even after 40 million years of cosmic ray exposure, you lose about 80% of the glycine. So this is something we're definitely going to need to pay attention to. What do we do about this? Well, one strategy is to drill near these scarps. These scarps are where you have a lot of wind erosion, and so you can get subsurface material exposed quicker. And so you kind of want to drill here where you think you have the least amount of ionizing radiation exposure. Or another strategy is just drill deep. Just get down below a meter to get out of this ionizing radiation zone. So we've seen these simple molecules here, but what we really want to look for are these more biological, biosignatures. I probably feel comfortable making the argument now that doing some of these analyses like we heard about in Jamie's talk is probably going to take sample return lab measurements. These measurements are extremely difficult to do in situ, but we're going to give it our best shot. One trick we have up our sleeve is a wet chemistry experiment in SAM. So 9 of these 74 cups have a wet chemistry reagent in them that can react with amino acids and carboxylic acids and make them detectable by GCMS. We've done one measurement on Mars of the soil. Unfortunately, I can't talk about those results at this point. They're not published yet, but I will tell you they're interesting, and there's probably more organic complexity than what I've shown. Okay, the future, real quick. ExoMars. I mentioned drilling deep. That's the strategy the ESA Roscosmos ExoMars mission is taking. They're going to go down to 2 meters to try to get below this ionizing radiation zone. At Goddard, we're building another mass spectrometer, an ion trap mass spectrometer, which is really cool. It allows us to measure even higher masses, up to 1,000 Daltons. But what makes this technique even more interesting is we have a laser instead of ovens to zap the sample. And we can see heavy organic molecules even in the presence of perchlorates without a lot of combustion and chlorination. That's pretty exciting. And then, of course, sample return, which I really hope we do someday. And Mars 2020, which is the NASA mission, is the first step of that. So we're going to go back to Mars, probably a different landing spot than Curiosity. Collect samples, put them in cores, seal them up, leave them on the surface for a future mission to come and get. One quick reason for optimism here. Jamie talked a lot about the amino acid analyses we've done in carbonaceous meteorites, but we've also done it on Mars meteorites. And this was a publication by Mike Callahan back in 2013. Didn't get a lot of attention at the time, but it's really a fascinating result. And we're actually finding Martian amino acids in this meteorite. These amino acids are straight chains, so they don't look biological, where you have a lot of branched, and they're all achiral. But wow, we can say with confidence now, we've got amino acids on Mars. Are they in the subsurface or on the near surface? Don't know. But this provides a wonderful kind of reference frame. This is what non-biological amino acid chemistry looks on Mars. So let's bring back those sediments and look for more complex materials. Okay, take-home message. This is all really hard. I do have time? Okay, I'm rushing. Okay, okay, good. Can relax a little bit. But this in situ analysis and search for organics, specifically trying to figure out the origin of this stuff is really challenging. Okay, we've marked off the first box, so we found the organics. Now I really feel like it's time, to get these samples back into Jamie's lab, so we can figure out if there was ever life on Mars or not. So this is all, really encouraging, but we've got some more work to do. There's just too many sources, too many explanations for what we see now in the data. Martian organic story continues to evolve. I mentioned the wet chemistry experiment, so we haven't given up on looking for amino acids on Mars despite the cosmic radiation. We're going to give it a try, and we've got some really exciting missions to Mars coming up that will help us get further along the path to searching for biosignatures. And I just want to thank you, and also it's been such an honor to be part of this great team. I mean, there were hundreds, thousands of people that made this mission possible. I'm just one of a few. Very fortunate to be involved in this mission and this discovery. And if you're interested in following Curiosity, there's a Twitter feed, Facebook, all the social media. You can stay as up to date as I am, frankly. Everybody thinks we're hiding pictures and stuff, and no, go to these links, and you're basically seeing everything we're seeing. So it's pretty cool. Thank you. No problem.
Rob Malechko from MSU. What's the counter ion on the perchlorate?
So we think it's either magnesium or calcium.
And then
mainly, a lot of that's based on the Phoenix data.
Then, sort of a related question is: have you found any chlorinated benzoic acids or carboxylic acid substituted benzenes? If per the hypothesis that that's where they're
so I didn't show it here. We found some dichloroalkanes, not carboxyl, dichloroalkanes, C2, C3, C4. We find chlorobenzene and dichlorobenzene. Chlorinated carboxylic acids, not yet. But that carboxyl group is the one that can easily be chlorinated. So we may be losing those in some of these. My feeling is we probably got carboxylic acid like.
So you showed a trichlorinated benzene. Is that also?
Yeah.
Okay.
Chloro, di, tri, and tetrachlorobenzene as well. Let me see them all. Yeah, if you can chlorinate these things, perchlorate will do it for you, basically.
So up to 4 chlorines, but not the 5 or 6 that you might see from chlorination of the maleic acid?
Yeah, good question. I mean, right now we've got up to dichlorobenzene, but the abundance falls off pretty drastically. So I think we're just reaching our detection limit. I would think that they're in the gases, but we're not able to see them with SAM. So we can see up to dichlorobenzene.
Okay, and if these were actually the acids, they'd probably be in the salt form, and you probably wouldn't see them because of the way that the whole pyrrolization method works. Is that correct?
We won't see maleic acid itself. We would see CO2 from it, from thermal decarboxylation, and some of these simple chlorobenzenes, but no, we won't see. For maleic acid, you'd need a technique like MOMA with a laser desorption to see it in its native form.
Okay, so that's kind of a partial answer to yours, is they don't have the capability to see the acid itself.
Now, the wet chemistry may help us. There we can actually derivatize carboxyl. Maleic acid's going to be tough because there's so many, MTBSTFA can derivatize on all 6 acids. But simple carboxylic acids, we should be able to see.
Can I ask one last question? So for the dichlorinated benzenes, do you see ortho, meta, and para?
Yeah, we see ortho and para.
So I have a question about how these missions are planned in terms of experimental design. What goes into that process when you realize you only have X number of vials that you can do chemistry in, and you've got only X liters of solvents you can work with, and you've got only so much power, and you want to explore? And how do you prepare for the unknown discovery or unanticipated event that you would then want to explore further? Do you simply have to say, I can't do it, and that's it? Or can you plan for that?
Scientists rarely say we can't do something. The engineers often tell us we can't. But no, we like to try new things. And actually, there's a lot of flexibility built into SAM that I wasn't really able to get into the details. But just to give you an example, when it was designed, we didn't even know that we found out about perchlorates on Mars after SAM had already been designed. So this is a discovery that we've had to respond to. And it turns out, perchlorates are not very good for pyrolysis. You need wet chemistry techniques. So had we have known this in advance and had the time, I mean, these things it took 10 years to build SAM from proposal to, if we had had the time to know, we could have designed some of these things and maybe included more wet chemistry capability on SAM if we had known about perchlorates. But it's hard, even on a daily basis. I mean, we're limited in resource. We have helium that we're losing. Our pumps are eventually going to die. And so we got to be very careful now. We just have a new drill hole on Mars, and we're going to have a whole discussion probably in the next few days about whether we actually want to do a GCMS analysis. You know, it's hard because you know it's a new drill hole, and you're going to want to do it. But you got to weigh this against, hey, we're taking life away from SAM when we do this measurement. And again, this is why sample return is so important. You never have to have the arguments like this. You know, I mean, you bring it back. You've got to archive some for the future, but usually you have enough material to do what you want to do, and change the technique, change the method. You can talk about more in the panel discussion if you want about this, but it's so much easier if you can just do these analyses in the lab.
Is this on? Okay. Just curious about what you said about the 80 million year cosmic ray exposure ages on a 3 to 4 billion year old rock. Does that mean that the rock was recently excavated and exposed? Because that would kind of surprise me, but maybe that's what
exactly.
it's saying.
So I didn't get to show Yellowknife Bay. There's some really neat pictures of it. If you go online, search Yellowknife Bay, and you can see that there's actually, it's a kind of a delta, alien fan. And at the edge where we were drilling, there's a scarp. And so it's basically a little ledge, and the wind is basically just eroding the stuff back, essentially bringing subsurface material to the surface faster, if you want to think about that. But yeah, the stuff that we were drilling in the top 5 centimeters had only been, at some point 80 million years ago, that was actually a meter below the surface, but has been excavated by wind erosion.
Cool,
Yeah.
Thanks.
Okay, I have one last question. When you were talking about the PAHs that were detected in the meteorites, how big were they?
I think the biggest one I showed up there, so definitely there was pyrene, 202.
Right.
I think there was 278.
Okay.
I don't know. I'm working from memory now. I have to go back to my slides.
Right.
But.
Was that the biggest you looked for?
So we didn't do that work, just to clarify.
Okay.
That was Simon Clement and others
okay.
at the Johnson Space Center as part of their 1996 science paper.
Okay.
Yeah, we didn't do those studies. But again, I think the conclusion there, Andrew Steele did some of those measurements and saw the same kind of pods associated with these magmatic minerals. And so the idea is that these are probably not products of biology. You can never rule it out 100%, but a high temperature origin is also quite possible for these. So.
Right. All right, thanks. All right, let's thank our speaker. And we have a break until 10 o'clock.